We continue with one of the most important topics in business calculus, the topic of optimization. In section 3.5, we will be looking at applied optimization problems. We'll solve problems using calculus and use optimization to solve inventory control problems. So what is optimization? Well, optimization is the process of finding the absolute extrema of a situation. And you can think of the business type applications that you'll use this on, from finding the maximum profit to the minimum cost. And then there's other ideas that this applies to, and we use calculus to solve those. So here's the general strategy for solving an optimization problem. Number 1, read the problem. Number 2, draw a picture, if appropriate. Number 3, create variables and describe them verbally with words. Number 4, create the equation to optimize and find any constraint equations. So this is the one where you create the equation that you want to find the maximum or minimum value of. You'll read the problem to figure out which equation that should be. And then if there's anything that's constraining that equation, you'll write those equations down as well. Number 5, reduce the optimization equation to one independent variable. Number 6, use the extreme find the extreme value of the optimization equation using the extreme value theorem if there are endpoints to the domain, or you can use the second derivative test. And then number 7, interpret the results in the terms of the problem. So example number 1, a farmer has 60 feet of fencing to build a rectangular pen. What is the maximum area possible? So we're going to have a rectangular pen, like so. And let me go ahead and denote the length as x and the width as y. And so the sides across for those are the same as well, x and y. That was step number 2. Step number 3 is to describe my variables verbally. So x is the length, y is the width, and what else do I need here? Well, the farmer has 60 feet of fencing. The fencing is what goes around to create the pen, so that must be perimeter. And then the question is, what is the maximum area possible? So I definitely need area. And area is the one I'm trying to optimize, so maybe I'll put a little star there. All right, step 4, create the equations. So the optimization equation is the one that I want to find the maximum of. So that's the area equation. And since I have a rectangle with a length of x and a width of y, the area is just x times y. Now, I can't just build as big a pen as I want. I have to satisfy some kind of constraint. And the way to think about a constraint is some sort of limiting factor. I can only build it so big because, and then whatever the reason is, that's your constraint. The reason here is because I only have 60 feet of fence. So the constraint in this case is the perimeter. And the perimeter is 2x plus 2y. There are 2 x's and there are 2 y's. And so you just add them up. You don't really need to memorize the formula for that because you're just adding up sides. And how much fencing do you have? You have 60 feet of fencing. All right, step 5, reduce the optimization equation to one independent variable. So notice here that the problem is I have an x and a y, and I just want one of those. I'm going to try to solve and get rid of the y. And to do that, you need to solve the constraint equation for y. So I'm going to take the 2x from the constraint equation and move it to the right side. Then I'm going to divide everything by 2. Now, the relationship between x and y is that y is equal to 30 minus x. So I can take this and I can substitute that into my a function and get x times, and here where the y was, I'm now going to put in 30 minus x, because that's what y is equal to. Now, in the process of doing this, notice that I have eliminated all of the other independent variables except for the x. That makes area a function of the x. I can determine the exact area of this rectangle simply by knowing the length, because of the constraint that says the perimeter has to add up to 60. Let's go ahead and simplify this equation. It becomes 30x minus x squared. And now we perform step 6. You find the extreme value by using either the extreme value theorem or the second derivative test. I'm going to use the second derivative test. But in order to do that, I need the first derivative. The first derivative of a is 30 minus 2x. I need to find the critical values, so I'm going to set this equal to 0 and solve for x. And we get x is equal to 15. Now I'm going to take the second derivative, so I can use the second derivative test for extrema. And the second derivative of a is just negative 2. So it doesn't matter what value of x I had. Anytime I plug in an x value, I'm going to get negative 2. This is less than 0, which means that this function is always concave down, which means that the critical value that I found was an absolute max, because it was the only critical value for this problem. Now the question was, what is the maximum area? So we know that x is equal to 15 produces the maximum area, but what actually is the maximum area? So actually this is now number 7. Let's erase this. That was still part of 6. So here's number 7 now. So we're going to take a of 15, and we're plugging it into my original a function, which is either this one or this one, your choice. I'll do it to this one here. 15 times 30 minus 15 is 225. This was in feet, so this is feet squared. So the maximum area of the pen is 225 square feet. Problem example number 2. A farmer has $6,000 to spend on building a fence for a rectangular garden. One side is made of special electric fencing and costs $12 per foot. Other sides are regular barbed wire fencing and cost $4 per foot. Find the dimensions and area of the largest possible garden that can be enclosed for $6,000. So again, let's start off by drawing the picture of the garden. It's a rectangular garden. Now this one is a little special because one of the sides has the electric fencing on it. So I'll put little shocks here, like that. And it doesn't matter what we call this side. I'm going to call it X. And then we'll call the other sides Y. And the other sides just have barbed wire on them. So put little barbs on them here. Like so. Now, let's identify some of my variables. So the X, again, is going to be equal to length. The Y is going to be equal to width. And I don't have a perimeter this time, but I have a cost. So C is going to be equal to cost. And I'm still trying to find the largest possible garden, so that's area. And so we'll use A for area. All right, so that was step 2, step 3. Here's step 4. Find the equations. So the optimization equation, again, we're trying to optimize area. We want the largest area. The constraint that I have is that I can only have $6,000 in cost. So what is the equation for my cost function? Well, it's going to cost $12 per foot for the special electric fencing. This is the electric fence side right up here. And so there are X feet of electric fencing, and it costs $12 per foot. So that's going to be 12X. Then the other sides are just standard barbed wire, and they cost $4 per foot. But how long is the fence that contains the barbed wire? Well, it's Y plus X plus another Y. And altogether, that's equal to $6,000. Now, notice how I didn't try to do anything fancy and try to figure out perimeter or whatever. I just added up the sides that was the barbed wire, and that cost $4. And I took the side that was an electric fence, and that was X, and I multiplied it by $12. That was it. Nothing too fancy. All right, now we have to do some simplifying. So step 5, let's simplify the cost function here. So this is going to be 12X plus 4Y plus 4X plus 4Y is equal to 6,000, which gives me 16X plus 8Y is equal to 6,000. I'm going to do the same trick as before. I'm going to solve for Y. By moving the 16X to the right side and dividing by 8. So 6,000 divided by 8 is 750, and 16 divided by 8 is 2. So here's the equation that gives me the relationship between X and Y. And now I'm going to plug that into my area formula. So again, I had a Y right here. That's going to be substituted out with what we have now for Y, which is 750 minus 2X. So this is 750X minus 2 times X squared. We need to find our critical values, so let's take a derivative. So we get 750 minus 4x, set that equal to 0. And we get x is equal to 187.5. We need to verify that this is in fact a maximum. So I find the second derivative. The second derivative is equal to -4. That's a constant. It's always negative. Therefore, it is always an absolute maximum. Now the question asked for the dimensions and the area. So we know that the x dimension needs to be 187.5 feet. To find the y, I'm going to plug it into my y formula that uses the x. So this is 750 minus 2 times 187.5, and that's 375. And we can put feet on that, feet. And then the last part was to find the area. Well, you can just multiply these together. you multiply them together, you get 70,312.5 square feet. Example number 3. A promotions company estimates that 200 people will attend a certain concert if the price per ticket is $18. For every increase of $2 per ticket, they estimate that 12 less people will attend. Find the optimal ticket price to maximize revenue from ticket sales. How many people will attend the concert? All right, so one of the things I like to do with this problem is sort of examine what's happening with the numbers here. And the way we do that is we're going to create a table. So there's no picture to draw. Let's just talk about what X represents. X is going to represent the number of changes that we make to our price and our ticket revenue, our ticket sales. Okay, so I'm going to make a little table here, X, and then people, and then ticket price, and then my revenue. Now, when we start out with no changes, we're told that 200 people will attend the concert if the ticket price is $18. And that gives me a revenue of $3,600, right? 200 people, $18 a pop, $3,600. Now, if we change the ticket price by adding $2, so here's one change. One change adds $2 to the ticket price, so it changes it from $18 to $20. Then the result is that 12 less people will come. So 200 minus 12 is 188. And I raised the price, but I lost people. So what does that do to my revenue? Well, it actually makes the revenue go up. And so we know that we're sort of on the left side of the revenue curve here because my revenue is still increasing. So we want to find that magic number of spots where we can increase the ticket price to a certain amount, and that will lower the number of people, but it will maximize my revenue. Let's give this another go with two changes. I add another $2 to the ticket price, and that subtracts another 12 people from my attendance, and revenue is still increasing at that point. All right, so we're going to need to use calculus to figure this out. And it may not even be an integer where it does this. So let's just go ahead and extrapolate what happens if I just call this X. Well, for the ticket price, we started out at $18, and we add $2 for every change. So that's 2X. And for the number of people, we started out with 200 people, and for every change X, we lose 12, so that's minus 12X. And if you plug in 1 and 2 for these X values, you'll see that you get the numbers from the table here. Now revenue is still going to be 200 minus 12X, that's my number of people, times the ticket price, 18 plus 2X. And now this is the function that we want to maximize. So revenue is equal to 200 minus 12X plus times 18 plus 2X. Multiply this out. I've already multiplied it, so you can double check it if you'd like. But it does equal 3,600 plus 184x minus 24x squared. Now I need to find the critical value. So I take the derivative. The derivative is 184 minus 48x. To find the critical value, set that equal to 0 and solve for x. And you get 23 over 6. We want to use the exact number here because it's going to make the other numbers come out really nice in the end. All right, let's double check to make sure that this is a maximum. So I'm going to take the second derivative, and the second derivative is negative 48. That's less than 0. So that means we do have an absolute maximum at my critical value, which is exactly what we're looking for, the maximum revenue. Now, what is that maximum revenue? Well, let's figure out this question first. How many people are going to come to the concert? So the number of people is 200 minus 12 times x, but the maximum occurs at 23 over 6 for x. So if you work that up, you get 154 people. And what's the ticket price? So the ticket price is $18 plus 2 times x. So it's 2 times 23 over 6 added to 18. I have to do a little bit of rounding here to the nearest penny, but that's okay. $25.67. And if you multiply these two together, you get the total maximum revenue is equal to $3,953.18. Lastly, we want to look at a problem type that is known as inventory control. Basically, what inventory control examines is the necessity of a company to continuously order supplies, but knowing that every time you reorder your supplies, you have to pay a certain fee to get those supplies, aside from the materials themselves. For example, like if you're going to order t-shirts, you have to pay for the printer to set up the screening, right? The screen print. If you're printing off brochures, you have to pay someone to design the graphics and to actually set up the machines to print them and things like that. That's one side of the inventory control. You have to pay someone every time you want to reorder something. The other side of it is because your solution is, well, why don't I just order everything I need right now? If you do that, then you have to store the items, and there can be a cost involved in storing those items, right? If you look at the back of the McDonald's, they have a little storage thing for cups and napkins, but it's like a shed. It's not like a big warehouse. It's because they only keep so much on hand at any time because of the cost associated with storing them. What inventory control tries to do is find the balance between having to order too often and having to pay for storage versus not ordering too quickly and then not having enough on hand. So what we try to do here is minimize the cost involved in the whole process. So let's read the example. Example number 4. A fast food restaurant has a uniform annual demand. Go ahead and underline uniform annual demand because that's going to be important. Of 12,000 boxes of napkins with their logo on them. It costs $5 to store one box for 1 year and $50 to place an order for the special napkins. How many times per year should the restaurant order the napkins to minimize the total cost of storage and production? So I'm going to start off with X is equal to the number of napkins, boxes of napkins, per order. So we're going to, each order of napkins is going to be, each order is going to have X number of napkins, or X number of boxes of napkins. And then let's let Y be equal to the number of times per year to order. So you're going to order Y times a year. Now, let's interpret some of the numbers here. The first one is 12,000 boxes of napkins. So if I order X napkins Y times per year, that should be the total 12,000. So X times Y is equal to 12,000 boxes of napkins. I'm just going to call them napkins. So this is my constraint. Now, the other thing that we have an issue with is how many napkins do we have on hand in our store at any given time, all right? So number of napkins in store, right? Or in storage, you can think, right? Because they're there, we just have to access them at some point. So at any time, Well, the napkins are being used by our customers, but the question said that they were used at a uniform rate, right? It was a uniform annual demand. Uniform annual demand, in this case, means that we're using napkins at a continuous rate. So, if I draw a little graph of what this situation looks like, then when I order my napkins, I have X napkins, and I'm using them at a constant rate. And then when they get down to 0, that's when I want to resupply, and then they get used at the same rate. And then this just keeps on going, etc. So the question is, how many napkins do I have on hand on average? And the on average, we can use an average here because it's uniform, right? We can just say, well, it's just this all the time. And then that sort of compensates for when I have more versus when I have less, sort of averaging it out over the whole year. On average, the restaurant has X over 2, or 1/2 X number of napkins at any given time. And you can sort of see that. Let me explain it here. At this point right here, I have almost all X napkins. But at this point here, I have just the opposite. I have that many napkins left over that I just used from the first point. And so this sort of averages all out to the middle, which is 1/2 X. All right. So now let's create our cost function. Our cost function is composed of two different costs: storage cost plus ordering cost. So we're going to call this C. We'll just call it C for now. C is equal to storage cost. So it's $5 to store the napkins. And then how many napkins do I have on hand? I have 1/2 X. And so this sort of takes care of all of the napkins all at once, because it's the average number of napkins I have at any given time throughout the whole year, 1/2 X. Now the ordering cost, it costs $50 to place an order, and we're going to order Y times a year. So the ordering cost for the whole year is 50Y. Now we have the situation where, again, I have two different independent variables, and I want to get rid of one of the variables. So I'm going to take my equation that was the constraint, X times Y equals 12,000, and I'm going to solve it for Y. That creates the function C of X is equal to 5/2 X plus 50 times 12,000 over X. And then we can work this out. 5/2 X plus 50 times 12,000. So 5 times 12 is 60. And there are 1, 2, 3, 4 more zeros attached to it. So that is 600,000. I need to find the critical value, so I'm going to take the derivative. The derivative of 5 halves x is 5 halves. And the derivative of 600,000 over x is negative 600,000 over x squared. Find the critical value by setting this equal to 0. So I'm going to move the fraction to the right side. And then I'm going to cross multiply. So I get 5x squared is equal to 1,200,000 divide by 5. That's going to be 240,000. And take the square root. So x is equal to 489.90 boxes of napkins. All right. And you could argue that we should probably round, but we'll just leave it for now. All right, let's verify that this is in fact the minimum, right? Because we're trying to minimize cost. So I'm going to take the second derivative of my function. And the second derivative is going to be positive 600,000 times 2 divided by x cubed, and you can verify that. But either way, the top number is positive. The bottom number is positive because x is the number of napkins, and the number of napkins has to be positive. So this is positive. It's greater than 0, which means we have an absolute minimum because it's concave up. And the question was, how many times per year should the restaurant order the napkins to minimize the total cost of storage and production? So that's y. And so the equation for y based on x was 12,000 divided by x. So this is 12,000 divided by 489.90, which is 24.5 times per year. And if you work that out, it's approximately every 15 days. So it tells us that the storage is sort of more costly than the ordering. Otherwise, you would order less frequently than that. All right, thanks for watching.